So before, or the last stuff that we were saying. Geez. This is what I get for trying to use weird software. Before we were talking about how to build and evaluate propositions. What we are turning to now is relations between propositions. So two propositions are equivalent if they always have the same truth value. And we will write a triple line equals sign for that. So this is how we write P is equivalent to Q. I do want to make a quick note that I encourage all of you to totally ignore, which is that the difference between this thing and this thing is subtle and harmless to ignore. So I encourage you to ignore it. But in case you're not satisfied with that, let me try and say quickly that basically this thing means you're forming a proposition that could be true or false, while this thing means you're claiming that it's always true. So that is to say, P double-sided arrow Q is a proposition that could be true and could be false, and P triple equals Q is stating that that proposition is always true. But in practice, here's maybe something slightly more confusing. In practice, you pretty much just use this thing. So that is what we will probably end up doing. But for now, I'm going to use this because it's used by the book, and I think it's fine to use it in the context of propositional logic. And one more piece of terminology I want to introduce is a proposition that is always false is called a contradiction. So let's get some examples. So this is something that we were just discussing. We were saying that, and I encourage you to check this, but we were saying that the statement P implies Q is equivalent to the statement not Q implies not P. Maybe another example that we gave in the break is that P, if and only if Q, yeah, let's use a double arrow, why not? Is equivalent to the statement that P implies Q and Q implies P. So these are examples of equivalences. An example of a contradiction, what is an example of something that's always false? If you consider something like P and not P, I mean, if you want to get technical, and is only true when both sides are true. And in this case, both sides are opposites, so they will never both be true. So this is a contradiction. But I mean, we don't need to get that technical. P and not P, hopefully that sounds to you like nonsense. It's just never true. Okay. So here is a point of view that I want to encourage you to think about. I think it might help you understand how logical equivalences work. So think of equivalences as ways to manipulate logical expressions or propositions in analogy to the way that laws of arithmetic manipulate algebraic expressions. So let me give some examples to make this concrete. Because there is really a very good analogy here. I'm not claiming that it's the same, that you can take arithmetic and directly translate it. What I'm saying is a lot of the laws will look quite familiar. And I think that might make you more comfortable with them, for thinking about it from that perspective. So let's get some examples in here. And let me just say tables 6, 7, and 8 in section 1.3 in the textbook. You can refer to these tables for many, many examples. Those are good. I generally don't recommend that you memorize them because, first of all exams and homeworks are going to be open book, so you can just go look right at them. And, also it's not the most interesting thing. But I do want to give a couple examples to help you think about them. So, what are some examples? So here's a basic one. Double negation, if you take not P, this is equivalent to just P. Because each time you flip true and false, and if you flip them twice, you get back to where you started with, right? And this corresponds to negative x is equal to x, because the negative signs cancel, right? So hopefully this is familiar. This might even be intuitive. Something that is maybe slightly less intuitive, but you could probably figure it out if you thought about it for a second, is you have sort of distributive laws. So P and Q or R is the same as P and Q or P and R. And this you should think about as, in analogy with the arithmetic x of x times y plus z is equal to x times y plus x times z. So if you look at the expressions, exactly the same kind of thing is happening. But maybe here's a good note to make, that the logic version actually works both ways. So if we switch the roles of and or, we get an exactly analogous thing. But on this side, you cannot switch addition and multiplication. Does not work. So these kind of both correspond to this example. And one more example that will be, that is like one of the most important ones, or one of the more important ones, is De Morgan's laws. Which are about negation. So I mentioned that negation can be a little bit tricky once you start getting into more complicated expressions. And here is starting to be an example of that. So let me quickly pick up a question. Is there a form of order of operations for logical operators? Yes, there is. I'm ignoring it because I prefer to put in parentheses whenever it's not clear. And I basically would encourage you to do the same. But if you really are curious, you can look in the textbook and they will tell you the order of operations. Then you can save some ink and leave some parentheses out. But I will put in the parentheses whenever it's not clear. So De Morgan's laws are how to negate ands and ors. So if you have a statement like P and Q, what is the negation of that? So the way you do it is you distribute the not onto both terms, and you flip ands and ors. So the negation of P and Q, right, not P and Q, is not P or not Q. And similarly, not P or Q is equivalent to not P and not Q. So it works both ways. You just flip the ands and ors when you distribute the not. And these also have an equivalent on the arithmetic side. If you have something like x is less than y, this is equivalent to saying that negative x is greater than negative y. So if you change the sign, you also have to, if you negate both sides, you also have to change the direction of the sign. So this is another nice analog from arithmetic. So let's take an exercise, or let me recommend another exercise. Try to prove some of these. Which again, a simple way to prove these things is just to write down the truth table and observe that they're exactly the same. Or if you're not keen on truth tables, I mean, they're useful, but they're a little bit cumbersome. Something that can be easier, which I want to give a quick example of, is that you can use these equivalences to sort of transform one expression into another. So I think I want to use an example, this contrapositive equivalence. You can write down the truth tables and see that it's the same. That's a good exercise if you want to try it out. But there's another way to do it, which is just by manipulation. So I'm going to introduce some things that I have not used before. Maybe I will quickly justify them. So P implies Q is equivalent to not P, or Q. This is something that you can sit down and work out if you want, but basically, what I'm going to say is going to essentially amount to observing it from the truth tables. So, you can write down some truth tables and work this out. But the point is that this is only false when P is true and Q is false. So if P is not true, we saw that it's always true in that case. And if Q is true, we saw that it's also true in that case. So this is just kind of a concrete way of writing down an implication in terms of these other logical operators. And from here, we can do some just pretty basic manipulations. So I mentioned before that for all of ands and ors and if and only ifs, the order doesn't matter. So let's change the order to Q or not P. And then again, a simple example that we gave earlier was that a proposition is the same as the double negation. So let's change this to not Q or not P. And this last step, you may have to stare at it for a second to see what's going on. But what we're doing, so all right, let me write this down. This is order doesn't matter. This is double negation. And this is the first line backwards. So what do I mean by that? I'm taking this line and applying it in the other direction, but with different things. So let me break this down, or try to. Let me make this a black box, and this, a different. So these are different things, but they're just whatever. And if I do the same thing here, you can see that these have exactly the same structure. So I can take these blocks that I've made and translate them into an implication. So the implication should be this thing implies this thing, right? Because that's exactly what is happening up here. So let me erase all of that and just rewrite the boxes down here. These were my boxes, right? So this is what we are getting. And as you can see, that is exactly the contrapositive. So this is another way that you can work with these propositions using logical equivalences in very much, again, in analogy to the way that you use arithmetic laws to manipulate algebraic expressions. You can use these equivalences to manipulate logical expressions to produce new equivalences.